Hello everyone, and welcome to my first attempt at a Houdini tutorial. Today we are going to try to modify a POP DOP network, that's a lot of letters, and we are trying to take it from its normal behavior to a bit more of like a fluid or a fluid behavior, let's say. And the idea is to basically leverage the microsolver to project the divergence and to get a more fluid result out of that. Let me show you directly what's it's supposed to look like. Okay, so let's say you have a very basic simulation like that, like pretty awesome test geometry, but the simulation itself pretty boring, let's be honest. And you are actually aiming to have something that looks more like this, right? So that's the main goal that we are trying to achieve. And I know that a lot of people will probably say like, oh, I mean, we can do that. We can do that without going to your strange system and just use the pop attack by volume. And fair enough, that's probably a good way to achieve this kind of result, generally speaking. I'm not even pretending that this is better. This has some advantages and probably some disadvantages as well. But the main reason why I want to make this tutorial is because I see a lot of people becoming more and more comfortable modifying subs networks and everything, which is great. Keep at it. But I don't really see that kind of comfort coming to DOPS very often. So that's kind of what I'm trying to get, right? It's to just encourage people to do the same with DOPS. Yes, we can modify DOPS just kind of the same way we do with subs, and there is no real reason to be afraid of those. So that's the general idea. Okay, so just before we start in Houdini itself, there is one thing that I want to talk about a bit more, which is the idea of projecting divergence in itself and what it means, like very broadly, because I'm gonna that's gonna be the main component of this set. All right. Okay. So let's say that you have a simulation happening in a domain. So you have your domain here. Cool. And even without thinking about density or anything, let's assume it's air or something. But let's say you have a velocity field going, very straightforward, just everything is pushed that direction. You can definitely do that in Houdini if you want. But if you do that, like everything will certainly move to the right, that's for sure. But if you start to consider what would happen in the real world, you sort of have a problem because in the real world, if you do that in a closed system, that is, there will be like a void creating in here, right? Because all the matter will be pushed there, and it will be a lot of compression going on that side. And when you have this kind of situation, like a void or a compression or something, you have what we call, generally speaking, divergence happening. And we try to avoid that because in the real world, if that were to happen, you would have the matter compressed here being pushed like first on the top and then on the side, and basically everything will try to reach some sort of equilibrium because compressibility has its limit. You cannot compress forever, and if there is void somewhere, like the matter will tend to try to go there, and so on and so forth. So basically this, what I just draw there, like try to approximate in a very rough way, is removing the divergence. So there is a node for that in any project, non-divergent. It's trying to make the velocity field non-divergent, so without any of those pockets of void or compression. Basically, like the pressure goes away. So that's what we are trying to achieve, uh, and that's the idea behind divergence removal. All right. So um, I think we can probably start building that in Houdini. Okay. So here we are in Houdini. And let's start very simple with a file. Cool. Load some great test geometry. Amazing. And let's start by creating a very basic, scatter on top of that. That will be used as a source. Cool. By density, that sounds all right. Let's not relax that. Don't really need it. And let's change it per frame. Awesome. Okay. So we have something. We will need some velocity. I want velocity going outward of the surface. So I will just create a normal node to have normals. So now I have normals here, and I will, in a wrangle, push this normal into the velocity. Okay, so now here we have some velocity going outside of the surface. Cool. So that's one thing. And let's use the point velocity node to, well, keep the incoming, but add some curl noise. So we have something changing over time. That would be pretty nice. Okay, so that's like a very basic sourcing. And now let's jump into DOP directly. I will plug my points into the first input and my geometry into the second so that we can use it as a collider. I will start by that actually, static object, so it's out of the way. DOP xgeo, this node, second input. Okay, so we should have our geometry coming in. Cool. I will use the surface collision for that. Okay, but that's secondary. What we actually want to work with is a pop object. So let's create a pop object. Okay, so if we check now in the geometry spreadsheet, we have our static object, don't really care about that, just for collision. And we have our pop object, and it already has a check for geometry. We will plug that into a pop solver pretty logically. And in this solver, we will also make a pop source. Let's see what it looks like. Not scatter on surface, but all point. From the first context geometry, we will guide. Okay, so we already have something. We almost already reached the boring state of what I presented earlier. I will just make it velocity. So we have a very basic simulation happening, short lifespan. Just for some visual interest, I will add some colors to that. In ramp, by default it goes to NH, which is great. I will use the black body and reverse that, so it starts bright and end up darker. Okay, cool. Almost there. The boring part is almost done. We just add the pop force going up, just to mimic kind of the buoyancy that would happen in a file. So just 10 units up and everything is going up. So that's pretty much the boring part done. Okay, so now what do we want to try to do with that? As I said, the idea is to remove the divergence. So let's type divergence and see what we got. We have multiple gas project non-divergent coming in. I suggest to use the multigrid. It seems to be the easiest, both the easiest and fastest, basically. But so if we look at that node, what we see is that it's expecting a velocity field. That's what it's acting upon. It cannot act on point. Point are sparse, volume are continuous, sorry. And that's what we need for that node to work. And we don't have that. So let's create that. Let's create a vector field and add it just directly below the pop object. So if we check now in the geometry spreadsheet, we can see that we have this vector field here coming. So that's great. There is a bunch of options here. I will not go too much into detail. The most important one will be the size. That will change the computation speed, obviously. And the name is quite very important because you can see all the volume are there by name. So I name it Vel, perfect. I will also add a visualizer to that, so it will make our life easier to understand what's going on. So let's do a vector field visualizer. Go. Let's show it because that's why we created it. Bounding box sounds nice. Ashes, great. Smokes, no, because it's a velocity field. I know I will need to use streamer. I will also change the resolution to avoid being too overwhelming, and visualization type I will put at speed. So we can now see our field there. Brilliant. We have something. It's very tiny, it's very empty, it's not super useful right now. What can we do with this? First, we will resize it to actually encompass the whole data we need. So let's do a resize field. I will plug it into a merge here, and I will put it in a specific order with the rest of the solver. Keep in mind that DOP network always evaluate from left to right, top to bottom. So when you reach a crossroad like that, it will start by taking this one, and then it will go this one, and this one, and this one, and then it will only go lower in the solver itself. So okay, gas resize field, very nice. What field do we want to resize? Well, reference, geometry. Oh, it become very tiny, but yeah, it seems to follow the simulation now. Great. I will add some bounds because it's always good to have some padding to be able to manipulate, especially when you remove the divergence as you saw in my little drawing. You kind of need some room to push stuff around. So some padding is always welcome. Cool. So now it has the right domain. Perfect. But it's still empty. So let's push some data in it. And there is a very important microsolver here, which is the particle to field node. Gas particle to field literally let you push an attribute into a field. There is other mode of using that node. I will show one later, but let's start with the basics. So we want destination field to be vel, and the attribute v, and oh, what do we see? What pushed in the field. That's great. That's cool. So does that mean that we can now remove the divergence out of that? Absolutely. Absolutely. And I will just take the note I created earlier, the project non-divergent, and I will plug it. And what do we see? Exactly what I described. So basically, it will tweak the velocity field to make it behave in a more physically normal way. So as you can see, like all the data, all the matter that is pushed in a way cannot really create a compression. So it's pushed on the side that will then go back up into the void that is created, and so on and so forth. And okay, that's all good. Like we now have a pretty cool particle and push it into the velocity field and remove the divergence of it. Amazing. But doesn't really change our point. It doesn't, and we just need now to push the value back from the volume to the point, and it's basically the opposite operation of the gas particle to field that we have here, and pretty normally it's named gas field to particle. And if we put that there and say we want the attribute B being sending the source field vel, what we know is by particle being in more fluid way. Our job here is done, right? So that's pretty cool and all. That's the gist of it. I'm not gonna lie, that's the main thing I want to show with that thing. So each step, the velocity field will be completely replaced by the velocity from the particle, and this will happen each step, which is nice. But we can do more. So as you notice, it still goes up, right? So it means that this pop force still applies. So what happens is this change the velocity field, the velocity attribute of the particle, and this remove the divergence out of it, and then the pop solvers just receive a velocity on the particle and will do its solver job, which is integrating the velocity into the position, and it will move the particle around. So you can keep using all the particle force you want. They will be obviously modified by what we just did, but it's not going away. But no, we have opened the door to something very interesting, which is using the gas microsolver, like all the microsolver that you can use in a pyro simulation, for instance, or a flip simulation. And let's have a look at that. Like one very interesting one, I think, is the turbulence one. Gas turbulence. Let's have a look at gas turbulence. One thing, if you start doing that kind of modification, that I can recommend is always check the binding tab, because the binding tab will basically tell you what this node is expecting. And you can see here it's expecting density field and velocity field. The stencil field is another topic altogether. Doesn't really matter in our case. But we have a velocity field, which is great. We don't have a density field though. So if we plug that in and we ask for the visualization, nothing happens. The visualization is not anything. Because basically turbulence uses density as a sort of a mask. So if there is zero everywhere, which can be assumed value, turbulence will not happen. But we can create that density field. We can create a scalar field. Density is just a single value, so we don't need a vector field. The scalar field is enough. And let's call it density. Okay, so now we should have in the geometry spreadsheet a density field, which is a scalar field. Awesome. Still nothing happening with the gas turbulence. I will cheat my way out of it just to show it. I will cheat it by putting an initial value of 1. Which will basically means that everything will be 1 everywhere outside of the bound, because that's the assumed value everywhere. So basically, now you have turbulence happening everywhere, which is nice. It's a very straightforward way to do that. In the case of turbulence is kind of realistic anyway. You tend to have turbulence everywhere will work. So there is that. That being said, I will still show you to make it a bit more specifically, because there are an interesting bunch of nodes there. Just like for the velocity field, I will create a visualizer to help debug that. So scalar field visualizer. Okay. Show guide geometry, yes please, bounding box, hash, and use smoke. And yeah, you can see that because I put the initial value at 1, I have 1 inside the domain, but I also have 1 outside of the domain in this case. But my domain is very tiny, so let's go to the gas resize field and tell it to resize density as well. Oh, if you spell it properly, that is cool. So okay, so we are resizing. So we have density everywhere, which I mean in this case of turbulence again doesn't really change much. But what I want to show you is that the gas particle to field node that we use once for the velocity before, we can use it for the density as well. But you are probably going to say like, yeah, but I mean I don't have a density attribute on that, which is fair enough. And the density in this case is not really represented by an attribute, it's represented by the presence of a particle at a specific spot or not. So you can use this node by unchecking the use attribute, and then it will just create the field and the data based on whether or not there is a. So that's pretty convenient. And now if we check turbulence visualization, you can see that it's using it as a mask, just like we would expect. Okay, So let me hide this and this. Okay, so now we have turbulence going on. Let me draw a frame. Cool. So now you can tell that you can start using both every pop force you ever had and all the microsolver that you could use, like disturbance, turbulence, you name it, you can use it. I just want to show a last specific one because I find it pretty cool, and also that it shows another node that can be useful in this kind of exploration. And that's the surface tension. Surface tension is also trying to mimic a natural phenomena that you can see a lot in liquid, but I would say that in some cases in gases, you can have some kind of the blobby behavior of flame that can happen sometimes in very specific case that these nodes can help reach. So I think it's an interesting one. So you can see though, this node requires surface field. And we don't have a surface field, so what do? We create a surface field. Surface is a scalar as well, so scalar field. We name it surface. Let's create a scalar field visualization for this one as well. Yes, show the guide geometry, please. Bounding box, yes. And that's about it because the default visualizer of a scalar field is actually sign distance field, which is what we are going to do. Just as usual, we are going to resize it. And no, we want to create a sign distance field based on the presence of the particle. So basically the same kind of thing we did for the density, but this node, as you notice, create like a float field. And if we want a scalar field, a sign distance field, we can use the gas particle to SDF. And it's basically preset by default. The only thing that it will complain about is that it doesn't have the p-scale attribute. So let me just create that very quick. P-scale equal CHF scale. And let's push a value of 0.1 on everything. Okay, so now it should stop complaining. We should start saying so in theory, we should be able to make the surface tension work. Let's plug it in and let's make a very strong value just to make it a bit more obvious. And I will also hide the visualizer. And we have surface tension. And you can see that the surface tension basically is making things clump around each other. So yeah. So I think that's pretty much it. That's what I wanted to show with this kind of technique, and I really want to encourage people to start modifying DOP a bit more. Like take that nice courage you found in SUP and just apply it to DOP. It's pretty fun. It's a bit mind blowing sometimes, mind bending or something, but it's really worth it. So give it a go, please. See ya.